Thank you, Don, and thank you very much to the organizers for this great workshop. And so today I'll be talking about some recent work with the Berkeley crew, so Luca Eliashiu and Pratik Rath and Patrick Tran, who's a student at Berkeley. And first of all, I see a few faces that were last week in Benasque, and I would like to partially apologize to them because a good chunk of this talk is an overlap with that, but there will also be a part that I didn't talk about, so hopefully I can wake you up when the time comes. So this is a long talk, so my plan is to start by giving you a broad overview of what's the issue and what are the interesting puzzles that can arise from the bulk side. And then I'll give you a quick summary of results, so so that you have a broad idea of what we're going to do. And then I will give you a little bit of review of the background of what kind of tools you need for this story. And then it will be I will go into some more detail of what exactly we did in this paper and this upcoming work that I a little bit optimistically put an August date there, but we'll see how that goes. So first of all, this talk will be focused on lower dimensional quantum gravity. Why is that interesting and important is because these lower dimensional gravity toy models led to a lot of progress in quantum gravity in the last maybe 10 years or so. And this includes a computation of the Page curve, for example, for evaporating black holes that could be done explicitly. And also it was helpful initially to compute indices using the gravitational path integral for supergravity and so on. And the reason why these successes were particularly striking is because these theories are generally well under control, at least some of them. In particular, the expansion that you get in the gravitational path integral in terms of geometries and different topologies is very well understood. And so non-perturbative quantum gravity effects can be studied explicitly. It's also useful that, at least for JT gravity, we know what the holographic dual of this lower dimensional theory is. In particular, it's some matrix integral. And this gives us, in the double scaling limit, and this gives us one more powerful tool to probe quantum gravity in this context. So this means that whenever we have some puzzle in gravity that can arise possibly in higher dimensions, what we can do is try and figure out if a similar puzzle arises in these lower dimensional models, and then use those tools to gain some intuition of what the solution is. It's sort of, let's say, our comfort zone. Whenever we have a problem, we know that we can try and solve it in these simple theories. So the specific theory I'll be interested in here is JT gravity. This is a two-dimensional dilaton gravity model. And this is the action for JT gravity, where this first term is a topological term. So you have this large parameter S0, which you can think of the background value of the dilaton. You have the Euler characteristic of the manifold where the theory is defined. And then you have a bulk term that I will discuss in a second, and a boundary term, which is the one that is really encoding most of the interest in physics. So if you do the path integral over the dilaton, oh, it's not working. Well, if you do the path integral over the dilaton, what you can see is that that imposes that the Ricci scalar is negative. It's a constant negative curvature. So you get hyperbolic geometries. Good. So you get hyperbolic geometries, and whenever you compute a quantity using the gravitational path integral, what you're doing is summing over all possible geometries with a fixed negative curvature and different topologies. Now, let me give you a simple example of this, which is actually an example that will be important for this talk. Say that you want to compute the partition function for JT gravity at some fixed temperature, so some fixed boundary length beta. Then that can be written as an expansion over geometries with different genus and a fixed boundary of length beta. And as you take the geometry with higher and higher genus, these geometries are generally suppressed by some factors of e to the minus s naught, where s naught is this large parameter. So this expansion is quite well understood in many cases, and so this gives us a way to try and understand these higher topology effects in quantum gravity. Oh, I should say, feel free to interrupt me at any point. It's a long talk. Would be very happy to have a lot of questions and discussion. So the first puzzle, I will introduce these two puzzles from the bulk side and then see how you can resolve them in this context. So the first puzzle that you have that arises in JT gravity, but it can also be seen as a puzzle that arises when studying non-supersymmetric near extremal black holes in higher dimensions. So you have, we saw here that you can compute this genus expansion. If you just keep this first term, so what is called the disk contribution, you don't consider higher genus, you can compute this partition function in JT gravity exactly. And this can be done because it turns out that all the physics is encoded in reparameterizations of the boundary, and that is weighted by what is called the Schwarzian action. And this Schwarzian path integral can be computed exactly. It's one loop exact, and so you can compute the disk partition function exactly. This was done, for example, by Stanford Witten. So what you get, if you do that, is something that goes like e to the s naught divided by beta to the 3/2. And then you have some other correction that for this talk won't be very important. So once you have a partition function, what you can do is compute an entropy. For example, you can compute the thermal entropy. Here I'll be focusing in this talk mostly on Renyi entropies, but these results also apply to entanglement entropies and to the thermal entropy. So for this Renyi 2, what you need to do is compute minus log of the ratio of two partition functions. One is a z, so a partition function with boundary length 2 beta, and the other one is a partition a product of two partition function with length beta. So pictorially, this is the idea. You have one disk of length 2 beta and a product of disk of length beta. If you do that and look at the beta, large beta regime, you get that the entropy goes like s naught minus 3/2 log beta. So this is telling you that if you try and take in beta large, so you look at very, very low temperatures, then this entropy goes negative. So clearly this is not ideal. And in fact, you cannot really interpret this entropy as counting any degrees of freedom, any microscopic degrees of freedom, because you get a negative number of them. And we could expect, so this is just a plot of what I wrote down here, and what you could expect is that maybe higher topologies become important. Let me try and give you a quick intuition of why, and then we'll see this in much more detail later. Well, the reason is that when you look at this disk contribution, you're really looking at some, let's say, semiclassical theory that has a continuum spectrum, but you're computing a partition function at very, very low temperature. So this means that this partition function will probably be dominated by eigenvalues that are very close to the edge, very close to the ground state. So it might be that you need some information about the, say, discrete nature of these eigenvalues near the ground state. And generally, these discrete eigenvalue spectrums are only captured when you look at a full quantum gravity theory, might not be captured in the semiclassical approximation of the theory. So this is just a rough intuition for why we could expect higher topologies to be important, and we'll see in more detail how this actually plays out. But it turns out that if you just look at these higher topologies, that's not quite enough to solve this problem. What you need is also some other contribution coming from connected geometries, let's say wormhole geometries, which also include higher topologies. Yeah.
I had thought that this issue was also believed to be connected to the difference between, I think they're called annealed and quenched.
Yeah, I'll get there.
You'll get there, okay.
Yeah. That's very important, but if you try to compute, say, the annealed or the quenched entropy or something like that, using only higher topologies of the disk, by that I mean only disconnected geometries, for example, not including wormholes between different replicas, that's not enough to solve the problem. Yeah. Yeah, I will have a extensive discussion of this quench versus anneal story. So from now, what I'm trying to do is just set up the puzzle purely looking at the bulk side without assuming anything about a dual theory, an average over an ensemble, anything. Just take the gravitational entropy, as Gibbons and Hawking would tell us to compute that, and you get that this becomes negative in the appropriate regime. So there is a similar puzzle, which is actually quite different technically, but it turns out that the similarities between the two are striking. And as you try and study this, you see that the solution to the two puzzles are also very close to each other. So this is a puzzle that arises when you consider JT gravity, including matter. This was done originally by Lyman, Dassina, Rosenberg, and Shan in n equals to super JT gravity in the BPS sector, but this can be formulated also analogously, just considering JT gravity, and it's a microcanonical band in the theory. So I will frame it mostly in terms of the second case, but this super JT is where it was actually initiated. So the idea is, whenever you have a two-sided black hole, you can think of that as some entangled state of two boundary theories. The example here would be the thermophile double state, where you have just no operator insertions if you have matter. You just consider an entangled state as some given, in thermophile double as some given temperature, and that defines a state dual to this double-sided black hole. And you can do also the microcanonical equivalent of that. So what you can do is take something very similar, but in the Euclidean preparation of this state, you can insert a bunch of operators. Let's say you take one given operator with some scaling dimension delta, which means some mass for the particle in the bulk, and insert many times this operator in the Euclidean preparation. So this tends to make the wormhole longer. That's at least a semiclassical intuition that you have, and this is what is called a partially entangled thermal state. And this thermophile double at a given temperature or at a given energy, if you are in the microcanonical case, is at that temperature, that energy is the maximally entangled state. Similarly, if you look at the BPS case, what you would get by the Euclidean preparation with infinite length beta, that gives you some state in the BPS sector, so at zero energy in the ground state of the super JT theory, would be a state which is maximally entangled within the BPS sector. So if you modify this state by inserting a bunch of operators, all you can do is lower this entropy. You cannot raise it. In fact, this can be studied specifically. What you can look at is, say, the entropy of one side, so the entropy, say, of the black hole, and try to compute what is that. So if you don't have anything, any insertions, you will get some entropy, which in the microcanonical case would just be the entropy of the black hole at the microcanonical energy. In the BPS sector, it would just be S0, the degeneracy of the BPS sector. But if you insert operators, you lower the entropy, and you can compute this exactly, and that's what I'll do in the next slide. So the idea is that you take k insertions of these operators, and the type of operators that you want to insert is an operator with some fixed scaling dimension delta, and then as you insert each operator, you want to project on the energy band that you want. So if you're in the BPS sector, what you do is insert an operator and project on the BPS sector. If you are in this microcanonical case, you would project on your microcanonical band after the insertion of each operator. Yes.
What's the spectrum of operators that you allow? Like any say I'm doing a random matrix. Well, in this way, well, okay, suppose I'm doing random matrix theory. Okay, the dual of SSS. So what operators do you allow as probes? It's kind of tricky to put operators in.
Yeah. That's, I will go into that later. Here, what I'm thinking about is the Ball theory. So say that you have JT gravity coupled to matter.
Okay.
And you have some operator, conformal operator with scaling dimension delta. So
I give you a specific operator, and you just put many insertions of that?
that's correct, yes. And you insert an operator and then project on the BPS sector or the microcanonical band if you're not in Super JT.
Okay, but then do you also coarse grain after that? Or because if I allow you one operator and two operators, and I just tell you how many operators are inserted, if I have two operators, there's an entropy associated with that, and in the first case of a single operator, there isn't an entropy. And it's a subleading entropy, but you could still hope to catch it. So just saying, so you need to give some more information about how many operators, or whether you coarse grain afterwards, or
I'm not coarse graining here. I just saying, okay, I insert a given number k of operators. I am actually do the computation exactly in the next slide, but I give you one operator scaling dimension delta,
okay,
and then you insert k of them, where between two insertions there is always a projector on the microcanonical band of interest. This is the setup.
Okay.
And then you can compute the entropy of the right side in the state that you obtain when you insert all these many operators k. And you can see how the entropy changes as you insert a higher and higher number of operators.
Well, that's what I'm not sure I agree with, because suppose I have two operators with dimension delta, then I can insert any combination of them. And and that will give me the same length. So it's the same gravitational background, but in one way of setting it up, it has no microscopic entropy, and in the second way of setting it up, it has microscopic entropy.
So you're saying if I have two different operators with the same scalar dimension?
Two different operators with the same conformal dimension.
You can have formulated puzzle also in that case. The specific behavior that you get is a little bit different.
But the gravitational background is exactly the same.
The computations will not be exactly the same.
In gravity, they wouldn't be exactly the same?
Well, it depends what you mean by different operators. If you give me an operator with the same scaling, two operators with the same scaling dimension, I assume what you mean is that they carry some index, maybe?
Yeah, psi1 and psi2.
Then the two operators cannot, when you do weak contractions, you cannot contract two different operators with each other, so the calculation will be a little bit different. It depends on which, only operators of one kind can contract with each other. And so you would obtain a slightly different answer. You can still do the calculation. In fact, we have a model in which you can do the exact what you're saying. So each operator that you insert has, say, a different index, and you get a different answer, which still has the same puzzle, just the details of the computation is a little bit different. Here, I'm focusing on the case in which I give you one operator of dimension delta, and you just insert many of them.
And that probably spans only a very small set of the field theory states that have the same length, right? Because, say in SYK, I can in principle have n species, and if you allow all of them to be inserted, it will be a real mess.
Yeah, in principle, you can obtain a lot of different states, but the idea, if you allow more and more operators, the idea in this case is just seeing how the behavior of the entropy on one side, what is the behavior of the entropy on one side once you insert all these operators to prepare some different state. And maybe in the next slide this become clear. Please feel free to ask me again if that's not. So we have this multiple insertion of a given operator. What you can do is then compute a partition function. You can think of it as the partition function for n replicas of the density matrix of the right side. And you can compute this thing when you have k insertion. So here I'm depicting a case in which you have k equals 2. So between each one of these cuts, you have one density metric for the right side. So for k equals 2, this will be given by some boundary which has 2k insertions, so in this case 4. And then you glue cyclically n of these. And this sets your boundary conditions to compute trace of rho with k insertion in the preparation of a state to the power n. Once you have this boundary condition, you can compute the bulk diagrams that compute this. And for these kind of rules were nicely written down in this paper. And if you take delta, so the scaling dimension of the operator, to be very, very large, at least in first approximation, this is not an approximation that is exact, but at least in the first approximation, you can neglect all intersections between lines. So the idea is that you want to only take pairwise contractions of these operator insertions and throw away all diagrams that include intersections. This is something that you can do. And so at the end of the game, if you want to compute this with these boundary conditions, you just have to count all the possible pairwise contractions between these operators without any intersection. That can be done explicitly, and the answer is given by the Catalan numbers, which is just some combinatorial factor. And then you have a factor of e to the s. In this case, for the microcanonical case, e to the s microcanonical, or if you had the BPS sector, it would just be e to the s naught. So given this, what we can do what we did before, compute the entropy for this right side. Yep. Non-crossing. So this is the infinite delta limit. With different topologies, yes, but here we're just doing a disk calculation for now. I will comment about that at the end of the talk. So in this just this calculation, just like before we did a disk calculation for the entropy, that's what I'm doing here too. And if you do that, you can compute the run-into entropy and get that is given again by S of E bar minus 3 half log K. So you see that this is very reminiscent of what we saw in the thermal case. So as you increase the number of insertions, if you insert more and more particles, you're decreasing the entropy. If you insert too many of them, something that goes like e to the 2s over 3, you get a negative entropy. So again, there is some seemingly some puzzle arising in this case. In the opposite limit, where you, yeah. Has the same origin? That's a good question, in the sense that in the previous calculation it comes from the while loop computation of the z. In this case, it comes from combinatorial factors of the ratio of Catalan numbers. So apparently not, but I think from the dual matrix model you understand that it actually does. From the bulk side, is definitely not obvious to me, at least. Yeah.
Can it be that you're overcounting the state? So this negative answer is because of you overcounting?
What do you mean overcounting?
So here, for example, what this CKN is computing is some sort of basis, the dimension of the basis, but
the CKN?
Yeah, the Catalan number.
This is just computing all possible contractions between operators.
So each one probably represents some independent topology or geometry.
No, this is no higher topologies, right? This is just a disk calculation so far.
But is that representing some kind of basis state in your geometry?
Maybe that is a way to think about it. You're sort of consider, if you insert, you can consider all states given by having 1 or 2 or 3 or n insertions, and that would generate some overcomplete basis. I think that is one way to think about it. And in fact, I think all this puzzle can be understood in terms of sort of a black hole information paradox. It's an information paradox in its similar to that. So I guess you can probably think of it that way as well. But this is just a calculation. You can just compute these correlation functions, and this is the answer you get for the entropy, using just usual JT gravity rules. Now, what you can do is also consider the opposite limit, so the very, very small delta limit. And in this case, all intersections are actually irrelevant. So you can consider all possible contractions. If you take the strict delta to 0 limit, and I will comment that this is not quite a nice limit, but what LMRS, that paper that I showed before, showed is that if you take this delta to 0 limit, all you need to do is compute all possible pairwise contraction, regardless of the intersections. I draw a couple of diagrams here just to point that out. And you get a different combinatorial factor, which is just a double factorial. And if you compute this, what you get is an entropy that goes linearly, decreases linearly with the number of insertions. So this means that while in this case you get a puzzle as long as you take the number of insertions scaling exponentially in the entropy, in this case it's enough to have a linear number of insertions to already get at least seemingly a negative entropy. And I will discuss this in more detail later, but the idea is that this is a consequence of this small delta limit being not quite right. If you want to take small delta, you really need to take a little bit into account the intersections, because if you take the straight delta to 0 limit, which is this, that operator would just become the identity. So that would not correspond to having any line at all. But if you take delta small but finite, then there will be a change in regime between this linear behavior and this log behavior, so the puzzle will again be at exponential number of insertions. Yes? Sorry?
In what you said so far, what is the importance of the VPS character of these states?
I don't think there is an importance. In fact, this puzzle, as how I am presenting here, I see even in JT gravity in a microcanonical band.
Because you said that you insert projections on VPS sectors in between the operators?
Or on a microcanonical band in JT gravity, not supersymmetric JT gravity.
But then it's not obvious that the operators are local in time, no? If you have these projectors.
Well, you can just define an operator to be a local operator insertion and then infinite Euclidean time evolution on the two sides, for example. That would be a projector on the BPS sector, right?
So is there an infinite time evolution between any two insertions there? Or?
Any two insertions here? If you're in the BPS sector, yes.
Ah, okay.
If you're in the BPS case. That's the way the puzzle was originally formulated by Lee, Maldacena, Rosenberg, and Shan.
Okay, so the pictures are a little bit confusing then.
Well, I cannot put infinite time evolution in between right. 2 points on a...
Sorry.
Yeah. But you can think of it as just having some projector inserted. Like, one way to write down the projector on the BPS sector is having infinite Euclidean time evolution. If you will, just consider this insertion as an insertion of a operator of scaling dimension delta times a projector on both sides.
Is your comment about needing to take into account some kind of interactions for delta goes to 0 the same as saying that the geodesic approximation should fail for delta goes to 0? Or is it different?
No, it has to do with the fact that intersections in JT are weighted by SIG-J symbols in general. And that gives you some dependence on, like, each intersection comes with some factor, which is not exactly 1, even if delta is small. It reduces to 1 as in the limit delta goes to 0, but that's not quite the correct limit to take. Okay, so these are the two puzzles. So we have a puzzle just in pure JT gravity, not matter, where if you compute the thermal entropy and you take the temperature to be too low, you get a negative entropy. From the point of view of this, if you have JT gravity with matter, a similar puzzle arises when you insert too many operators in the preparation of it, the state dual to a two-sided black hole. So given these two, what I want to do now is first give you a quick summary of what the results are. And then I will go, the next step is to review some background material that we need in order to understand and solve these puzzles. And then I'll tell you what we actually did. I will first solve the first puzzle, and then at the end of the talk, I will come back to this matter case, which is still a work in progress and a bit more involved than the other one. So it turns out that the reason, and this is a well-known fact, it's not something we discovered, the reason why this gravitational entropy goes negative is that it is what is called an annealed entropy. So it comes from the fact that JT gravity is dual to a matrix integral, so you need to average over the matrix integral whenever you compute quantities. And you can compute averages of different quantities and then take the corresponding average quantity and compute whatever you want. So if you average the partition function and then compute the entropy, you compute what is called an annealed entropy, and that's what we were doing. And that quantity actually needs not to be positive at all. And I will explain all this in more detail. What you would like, in principle, to compute is what is called the quenched entropy. So this is, you compute an entropy in a given member of the ensemble, and then you average over the whole ensemble. That clearly must be positive, because each entropy in the ensemble is positive. But from the bulk side, this is actually very hard to compute. This is a known problem that was studied by Younger, Fischetti, and Maloney. So what we did here is define some halfway quantity, which we call semi-quenched entropy, and show that this quantity has a positivity property, and then try to understand how this how this entropy stays positive, looking at the bulk side. So for a value of beta or k in the two puzzles of order e to the 2s over 3, you can solve this issue from the bulk side and see that what you need is both wormhole effects, so effects connecting different boundaries, and higher genus effects. You need a full resummation of the genus expansion plus wormhole effects. And it turns out that this matches what is called the area limit in the dual matrix integral, which I will review in a second. If you got even larger values of beta or number of insertions, you need, you cannot really do this from the bulk side, you need some boundary resolution. So you go into the dual matrix model and study what happens. And it turns out that the matrix integral has a completely new saddle, which was studied in detail in this context by Sergio Hernandez-Cuenca in his paper last year. And the idea is that you just have a completely new saddle for the matrix integral. From the bulk side, it's not fully clear what that actually corresponds to. And again, the entropy goes to 0 and matches smoothly what you get in this area limit. And in both cases, what is important is the intuition that I gave before, that you need to really look at what goes on near the ground state for the beta case, or near the highest eigenvalues of the matter operator in this matter case. So you need to really be sensitive to what happens near the lowest or largest eigenvalue and how the spectrum in that region is discrete. And finally, for the quenched entropy, so there is a well-known matrix model resolution of this puzzle. Just start from the matrix side, you look at the area limit of the matrix model, you can compute this quenched entropy, you get that it stays positive, everything is good. But from the bulk side, it's actually very hard to do. And the reason is that that involves some analytic continuation and some replica limit, which is not well understood from the bulk side. But one thing that we showed is that this one eigenvalue instanton, which this new saddle of the matrix model that Sergio introduced in the context of the quenched entropy, is actually not quite good to compute the quenched entropy. And the reason is that the saddle point approximation you use will break down. And I will discuss that a little bit. Okay, so this was just a bird's eye view of the story. Now I want to give you some background review of the material and then explain in some more detail what we actually did. So if there is any question, this would be a good moment to ask. Okay, so, oh yeah, I forgot. This is just a plot of the main results. So the annealed entropy, this entropy that we computed before, is plotted in green. This is the case for the thermal puzzle. The semi-quenched entropy, we see that agrees with the annealed entropy up to some value of the temperature which is low but not too low, and then the behavior of the two entropies are different, and the semi-quenched entropy we compute stays positive. So these two lines, green and yellow, are analytical calculation that we did, and this is what you get. And the blue line is what is called the quenched entropy, which cannot be computed analytically in this limit, but you can do that numerically. And if you do that, this is the answer that you get. It also stays positive. And the behavior as it goes to 0 is actually quite different from the one that you get from the semi-quenched entropy, but they both are still positive. The semi-quenched goes to 0 exponentially. The quenched goes to 0 as a power law. Yeah. So quench versus annealed.
Is there any intuition? Because, of course, annealed and quench,
Annealed and quench are very well known, spin glasses and so on. Semi-quenched, as far as I know, the place where I've seen it, not with this name and not in this context, but it's a place where I was going to comment on that later, but the place where I've seen it used is in random tensor networks. That's where people actually use that. And I'm not sure if it was used in something like spin glasses. I don't think so, but I'm not a huge expert in that literature, so I might be wrong.
So there's no clear intuition behind the...
Well, I wouldn't say there is a clear intuition about what's the physical meaning. I think the reason why I think it's interesting is because if you compute this quantity, you see that it has to have a positivity property, but you can also compute it from the bulk side. So that implies that it tells you something about what is saving the day from the bulk side, and we'll see that this is this resummation of a connected geometry. And so it suggests that probably also for the quench entropy, the initial calculation should be very similar. The difference is in how you analytically continue the result of that calculation. That's what differs between semi-quenched and quenched. And that analytic continuation is not well understood, but the fact that in the semi-quenched case, wormholes are what save the day suggests that probably the quench entropy is also the same. So if we figure out how to do the analytic continuation, probably this will give you a hint of what you need to include from the gravity side.
Right. Thank you.
When you say you compute numerically, that's just for the entropy, right?
Sorry, when you compute what?
I mean, you said this is some numerics?
The blue line is numerical. Only the blue line.
This is just for the entropy, right? There's no is there an analog computation with insertion of probes?
No, this is the thermal case. It's just the thermal quench entropy.
But in principle, if you want to do a similar thing for probes, you need to tell me how you insert the probes exactly.
Yes, I also need to tell you what is the dual matrix model in the presence of O, which is a bit of a complicated issue that we'll discuss towards the end of the talk.
Okay. So also this is for the GUE ensemble?
For this one?
Yeah, this numerics.
This result is not for the GUE. This is, technically this is for the SSS matrix model that I will review in a second for dual to JT gravity, but in this regime it doesn't really matter, because in this regime all these matrix models are just basically the Airy matrix model, because we are in the Airy limit of the matrix model.
Okay, there are some coincidences in when people do this sigma model approaches for spin glasses. There are some saddle points that you can identify that say control the spectral form factor at long time, but they kind of work for GUE and they don't work for anything else, and they are kind of unreliable. Is that related to this?
So if it's the spectral form factor, I think the difference, and I think in the next few slides it will become clear, but the difference is that for the spectral form factor, generally what you're doing is zooming in the bulk of the eigenvalue distribution. And that is not generic, right? Like the GUE or a different matrix model will have different bulk.
No, but the point is that sometimes you can think that you have identified them correctly using a saddle point in GUE, but if you go to GOE, the similar saddle point doesn't reproduce the right answer.
Right. But in that, I think in that case, it's important that
in the bulk.
You're zooming in the bulk.
Yeah.
While here, what we're doing is zooming in the edge. So this is the Airy limit, and that Airy limit is generic, right? Like that's just edge universality. So as long as you have a square root edge in your matrix model, this applies to GUE, to SSS,
but there's no analog that you can sometimes find.
Sorry?
Okay, thanks.
Okay, so now I want to give you a little bit of a review of the background of why you need to solve these puzzles. So the first thing I want to review very briefly, and many people here are sure much more expert in random matrix theory than I am, so I just want to give you the main ingredients that you need from to solve this specific puzzle in gravity. So what is random matrix theory? You can consider n by n matrices, and each independent entry of this matrix, by that I mean that you could have some constraint in the between the different entries of the matrix. For example, if you want an Hermitian matrix, not all matrix elements will be independent, but the ones that are independent, they are independently distributed variables drawn from some probability distribution, and this probability distribution defines your matrix integral. So what you do is defining a partition function, which is an integral over all these entries or independent entries of the matrix, weighted by e to the minus n times some potential. This is what is called the single trace potential, where you just have a trace of some function v of m. So what you can do then is also do a change of coordinates, essentially, that instead of integrating over matrix element, you just integrate over eigenvalues of the matrix. And this is something that we will use a little bit. If you do this, you get some effective action which has this potential term, which is essentially just this. And then you have a second term coming from the Jacobian of this change of coordinates. That's called the van der Monde determinant. Let me just give you a little bit of intuition about what's going on here. So you have a first term, you can think of it as some potential that pushes eigenvalues to be next to each other. So it tends to just push eigenvalues together. And then you have a repulsive term, which is this van der Monde determinant that arises because eigenvalues tend to push each other away. So you will have in general some equilibrium between this attractive and this repulsive force that would give you some distribution of eigenvalues. So this intuition can be realized explicitly when you take the Largen limit of this matrix model and you go to this a continuum approximation in which eigenvalues, discrete eigenvalues, are replaced by a continuum variable x. And then the matrix integral becomes a path integral over the spectral density. The spectral density is basically the function that gives you the distribution of these eigenvalues. And if you then evaluate the matrix integral in a saddle point approximation, you get a given distribution of eigenvalues, which is what is called the equilibrium distribution. It's basically what you get by solving the equations of motion with this attractive versus repulsive force. And you get this equilibrium spectral density that turns out to be uniquely determined by the potential and also to uniquely determine the potential. This means that if I hand you the potential, you know everything about the matrix model. And if I hand you this equilibrium density, you also know everything about the matrix model. Let me give you a simple example of this. This is what is called the GUE, the Gaussian unitary ensemble. So here you just have a matrix model with this, well, maybe the simplest possible potential you can think of. This is just a Gaussian. And this corresponds to an equilibrium density of states, which looks like this. So you have a square root of 4 minus x squared. This is what is called the Wigner semicircle. Now, this blue line is just this function here. And these histograms that you see here are just histograms that you obtain when you draw a lot of these matrices and then compute eigenvalues and then put them all together, divide them in bins. And you see that this continuum approximation approximates very, very well these many draws of the ensemble. So this specific form of the spectral density is typical of this GOE, but there are some features of this that are very generic, and I want to discuss those because they are really important for this story. So what is generic is what goes on near the so-called edge of this eigenvalue distribution. The fact that it goes to 0 as a square root is something that is generic for a lot of matrix models, including the one dual to JT. And this square root edge is exactly what will be important for our case. So to see that, this is what is called edge universality, and this statistics of the eigenvalues near the edge is controlled by some generic theory, which is not true only for GOE, but it's true for a lot of different things. In particular, you have this square root edge, and what you can ask is, okay, there is some probability of getting eigenvalues that are possibly even farther away than the edge, right? So this is just some saddle point approximation. You see that you have this sharp edge, but then you can study fluctuations. So what's the probability of getting eigenvalues even farther away than that? So to see that, you need to, say, zoom near the edge. That means that you first shift your variable to be centered on the edge, and then you take some scaling limit. The scaling limit is given by power 2/3 of n. It turns out this is a non-trivial result that was derived by Tracy and Widom. The intuition is that just that both the spacing and the fluctuations of eigenvalues near the edge are of order n to the 1 over n to the 2/3. So if you, in the larger limit, if you want to see these fluctuations, you need an appropriate scaling of the variable labeling your eigenvalue. So if you take the scaling limit, one very non-trivial result is that you get the area distribution. So what is that? This can be derived from the GUE, but it's generic for any square root edge matrix model. So the idea is that here yellow I plotted just a square root edge. So this is just a square root function. But the function that controls these fluctuations is something that looks like a square root, but then you have this small tail. So that tail gives you the probability of getting eigenvalues even farther away than the edge. And this is generally a very small probability, but it's non-zero. And it turns out that what we're doing is really probing this region. So why is all this matrix model stuff important and interesting? Yep.
So the fact that thank you. So the fact that the entropy is positive shouldn't really be dependent on the precise statistics, no? Entropy is positive just because it's positive. I could assume, for example, that at low temperatures I don't have the area statistics, but I could change my statistics and now have Poissonian statistics. Of course, the calculation would be different. But who ensures that JT gravity at such low temperatures follows random matrix universality? I don't know. It could.
Well, if
you
JT
could
gravity
define it in another way, and still the entropy should be positive. And so I'm just saying that. Well, here you are assuming this area statistics, which is already kind of an assumption, and the fact that the entropy is positive shouldn't really depend on that assumption.
Well, I think that if you assume or believe, I would say more than assume, that JT gravity is dual to a matrix model, and that matrix model is the SSM matrix model. That was actually my next slide. That matrix model is the SSS matrix model, right? So you have an equilibrium spectral density, which is given by this sinh function, and it has a square root edge. Then, if it's true that it's equal to this matrix model near the edge statistics is controlled exactly by the area distribution. So all I'm saying is that this is...
That I agree, but I could also, I mean, you could also consider, for example, saying that at exponentially small temperatures, the statistics of your Hamiltonian is like Poissonian, because there is a transition to integrability. You wouldn't see that anywhere else.
I agree, you could in principle, but actually there is pretty strong evidence that this is the correct way to think about it. I'll talk about this, because in fact what you can do is just do a Boole calculation, and do a Boole calculation that resums over the genus expansion, that's it, without any referring at all to the matrix model. And you get an answer that is exactly, including numerical factor, equal to the answer that you get by using the area distribution and computing the same quantity in this limit. So that's part of the resolution. This is something that was already known for the disk case in the for the resummation of all genus in the disk. This was studied by Younger, Fiscati, and Maloney, or at least reviewed by them. Someone else might have computed before. We extended a little bit that result to solve this entropy problem, but yeah. So why are matrix integrals important here? Because JT, as we were saying, is dual to what is called a double scale matrix integral. I won't go into much detail what double scale means, but what you can think of is that you have, in pure JT gravity, not matter so far, you have a Hamiltonian. The only observable is essentially the energy spectrum. So you have a random matrix model where the matrix that you're integrating over is the Hamiltonian. And you can think in this double scaling limit as the size of this matrix to be e to the s naught, where s naught is the small parameter in JT. Then Sash and Stanford showed that the corresponding equilibrium density states, which fully specifies this double-scale matrix model, is given by something that goes like e to the s naught times hyperbolic sine of square root a. So you see that if you take e very, very small, meaning that you are near the ground state, you in fact get a square root edge. You just get a square root a. So that implies that this matrix model has a square root edge, and the fluctuations of eigenvalues near there are controlled by edge universality by this ER matrix model that I showed in the previous slide. So what does it mean that this theory is dual to a matrix integral? It means that if you compute a quantity using the gravitational path integral in JT gravity, like we did before, for example, the partition function, what we are doing is, in the dual matrix model, is averaging this quantity. So in this case would be the partition function, trace a to the minus beta h, over the matrix model. So you have integral dh, you have this SSS potential, which can be derived from this formula, and then you have trace e to the minus beta h. Now, this, for some people, this could be a useful, I just want to make a comment, this could be a useful way to think about this. At the disk level, what you have is a continuum spectrum. And this continuum spectrum has some very small probability here. So what we're doing, so you have very, on average, basically in that region that we're really zooming in when you take beta very, very large, because we're really zooming near the ground state, you have an average number of eigenvalues over the ensemble which is smaller than 1. So that is one reason why you can think of that as the reason why this entropy goes negative, because you are essentially probing a region where the average number of eigenvalues over the ensemble is smaller than 1. This is one way to think about it, and I'll give another intuition in a second. So this is where all the story of anneal versus quench comes out. So we saw that in JT, what you do is average quantity over the dual matrix model. But now what we're doing is computing entropies. So when you compute entropies, you have a partition function, and then you take powers, ratios, logs, and you also need to average over this ensemble. And when you average, it really matters. So you can average before or after taking ratios, before or after taking powers, before or after taking logs, and all these procedures lead to different quantities. So the easiest one is the one where you compute the average partition function, z of beta, which is what we did before, just compute z of beta and JT, and then compute the entropy. So then you take powers, ratios, log. So if you do that, you define what is called an annealed entropy. And this is very simple to compute from the gravity side. It's just this partition function that we saw before that can be computed exactly doing the H-Workshop path integral. The problem is that this quantity actually is not positive at all. Like, it doesn't need to be positive. And one way to say this is that you can think of this quantity as essentially computing an entropy for a density matrix which is not normalized. It's only normalized on average. You can think of some density matrix rho tilde, which is given by rho divided by the average over the ensemble of tracer rho. So you can write down this quantity, and then that entropy that we are computing is just a trace of rho tilde to the n, essentially. So see that since this thing is only normalized on average, in general this can have eigenvalues even larger than 1, or in general doesn't need to be to give a result compatible with a normalized density matrix. And that's why this entropy can be negative. The quantity that ideally you would like to compute is what is called the quench entropy, which is you first, in each member of the ensemble, compute the full entropy, so log z of n beta over z of beta to the n, and then you take an average of that quantity over the ensemble. So this is clearly positive, because each entropy in each member of the ensemble is positive, and when you average, that remains the case. But it turns out that it's super hard to compute in gravity, because it requires an analytic continuation. And this analytic continuation is what is called a no-replica limit, in which you take first a bunch of replicas and then take the number of replicas that goes to 0. And in this regime, it's likely that actually the dominant contributions to the path integral are replica symmetry breaking effects that are not very well understood in gravity, and we don't really know how to do that. And this was studied in detail by Engeler, Fischetti, and Maloney. So what you can do is try and compute something which is halfway, which is what we call the semi-quenched entropy. And this is a case where you first take powers, then you take the average, then you take the ratio, and then you take the log. So the difference between the semi-quenched and the annealed is just that this power of n in the denominator is inside the average instead of outside. And that turns out to be enough to give you a positivity requirement. So this quantity must always be positive. And this is because z, just a triangle inequality, that z of n beta is always smaller than z of beta to the n, and in each member of the ensemble. And then if you take an average of both sides, this remains true. Yes? These things, yeah, it's a matter of like when is the entropy self-averaging, basically. That is true whenever you take beta small. Whenever you take beta small, so sufficiently high temperatures, these quantities, the entropy is self-averaging, and all these quantities agree. But if you start going near the edge, then you're really probing outliers in the ensemble. And when you probe outliers in the ensemble, you can expect the resulting quantities to not be self-averaging.
Okay, thanks.
Yeah.
I do Parisi replicas. What do I need to do in order to get the third quantity?
In the semi-quenched entropy?
Yes.
Yeah.
So, okay, the second one we know, that's like the full replica, symmetry breaking, everything. And what's the third one?
Yeah, in the spin glass, as far as I know, in the spin glass literature, this wasn't studied in particular detail. The only other place when I know this was studied was random tensor networks for gravity. So I don't have a good answer to that. The reason why I think it's interesting is because bringing this power in implies that in the gravity side, you will have some wormhole contributions connecting these different boundaries. And those wormhole contributions are actually exactly what you need to solve to have positivity. And since given this computation, in theory, if you can do an array continuation, you can compute the quenched entropy as well. This suggests that these wormhole contributions are actually what saves the day also in the quenched case. But that's one step too far. Like that's something we still don't know how to do. Yeah.
Sorry, can you repeat again? There is a, perhaps I misunderstood. Suppose you want to compute the S2 for the quench entropy, but then you said that it involves like the zero replica limit, but why is it?
So that's what's called the non-replica limit. The point is that you want to compute the log. So what you can do is, say that you want to compute log of z average. So the one way to compute this is take the limit for number of replicas that goes to 0 of average z to the m minus 1 divided by m.
Yes.
So you need to take, and if you want to compute that thing, you actually have really like that quantity. You have two replica limits where it gets a little bit complicated.
Okay. There's an extra replica index that it's not n. Like n you keep fixed, and then you add an extra one that you need to take to 0.
That's right. In gravity, actually, to compute that, you have 3 replica index.
Okay.
Because you also have to take basically z and beta times z of beta to say the k, then take the limit k that goes to minus n to take the ratio.
Very good.
And then you have this to do the log.
Thank you.
And if you want an entanglement entropy, you have a third replica index n to 1. Yeah. So this is the part that is confusing, because the usual replica limit, it's a bit confusing as well, but in gravity, sometimes at least we know how to do the n to 1 limit. This is the one that it's a bit more involved. Okay, so now we understand a little bit what's going on from the dual matrix model side. What we can do is try and look how to solve this issue. I will start from the first puzzle, which is a little bit easier maybe to handle, the one for the temperature. And let me just remind you that what happened is that if you just compute, at least at the disk level, this entropy, just computing the annealed entropy, now we know that's what we're doing, computing Z of beta average, and then taking powers, ratios, and logs, you get S naught minus 3 half log beta. So the entropy goes negative as you take beta order e to the 2 S naught over 3. Now, first of all, this e to the 2 S naught over 3 should ring a bell in the sense that e to the S naught here is the size of the matrix. And noting that this is the size of the matrix to the 2/3, which is exactly the kind of scaling limit that you need in order to look at the area distribution near the edge. So this is already a hint that that could be what's going on here. And from the bulk side, this can be understood very precisely. So we saw this genus expansion for the partition function, the sum over topologies with the same boundary length beta. It turns out that if you take beta of order e to the 2 S naught over 3, I will define here alpha to be the ratio between beta and e to the 2 S naught over 3, so it's some order 1 number. This genus expansion actually breaks down. So the leading order term in beta here is such that this genus expansion can be rewritten as a sum over genus of this order 1 parameter alpha to the 3g minus 3 half. And then you have an asymptotic expansion in 1 over beta for these quantities that actually don't depend on beta. Now, see that this asymptotic genus expansion now is not quite asymptotic anymore. The asymptotic expansion is a 1 over beta expansion, but this first part is actually order 1. So what you can do, turns out, is take the leading order, so L equals 0, of this 1 over beta asymptotic expansion. So here you just have a ZG of 0, and this infinite sum over all genus can actually be resummed exactly in this limit. This is a result that was well known, was done first as far as I know by Kontsevich and Okunkov, and this can be resummed exactly. So you have a sum for this leading order over all possible genus and gives you an answer which is e to the alpha cubed over 24 times some power of alpha. So this is the first part. Now, what we want to compute is this Renyi entropy, let's say Renyi 2. So in the denominator, we have the average of z squared beta, right? So this average of z squared beta will have two contributions. One comes from a product of two of these resummations. But then you have a connected contribution, you have a cylinder contribution. And this cylinder contribution has the same kind of behavior here. So what happens is, again, the genus expansion breaks down, but the leading order in 1 over beta, for the leading order in 1 over beta, this genus expansion can be resummed. So you have a sum over all cylinders with higher and higher topologies here. That can be done again exactly, and the answer that you get is this one. Now, it turns out that if you compute the exact same quantity, so z of beta or z squared of beta, in the dual matrix model, averaging where the dual matrix model is the Airy model, then you get the exact same answer. So you just take the dual matrix model, you take that to be the Airy matrix model that we saw before with that little tail, and compute trace e to the minus beta h average, and you get the exact same answer that you get, both in this case and in this case. So this is the hint I would suggest, like the, I don't know, you can call it a proof. I think it's a physics level proof of the fact that this limit of JT gravity exactly correspond to the Airy limit of the dual matrix model. Now, we have all these contributions, and we can finally compute this semi-quenched entropy in this limit. So remember, this was the log of Z02 beta over Z squared beta. This is just a Renyi 2. So this is written as a sum over all these genus expansions with a boundary of length 2 beta, and in the bottom you have a product of two of these expansions with length beta, and then this resummation over cylinder geometries. So if you do that, you get this answer, where the first piece you can think of as coming from this, and the second piece comes from the resummation of the cylinders. And as you take alpha large, so increase more and more the beta parameter, so lower and lower temperatures, this thing goes to 0 exponentially. So to gain some intuition, this is a plot of this quantity and this quantity. So this quantity is plotted in blue, and this resummation of cylinders is plotted in yellow. This is just the sum of the two. And you see that here you have 1 over alpha. So you see, so it's basically the temperature. As you go if you go to lower and lower temperatures, the cylinders starts dominating. So it starts taking over the behavior that you get from just a product of two of these resum disks. And this is what this error function comes from. And this error function takes over as you take the temperature smaller and smaller, and leads to this behavior. If you just drop this term and you just consider a product of two disks, you get only this first term, and the entropy ends up going negative. So this is exactly what happens when you take the annealed entropy and include all this genus resummation without including connected contributions. That gives you still a negative entropy. So you see that genus resummation is not quite enough to solve the puzzle. What you need is really the fact that we are averaging z squared instead of just z. And so you have this contribution coming from the connected geometries. So these higher genus contribution do become important for both quantities, but only for this wormhole contribution that are not present in the annealed case are really what allow this semi-quench entropy to stay positive. And we can hope that we can suspect that at least that is the case also when you compute the quenched entropy, if only we were able to do the appropriate analytic continuation in the no-replica limit. This is just a plot that should be for this quantity, annealed and semi-quenched. Now, let me just comment that there is a very interesting paper by Sergio Hernandez Cuenca, Nico Valdez-Meller, who's a student at MIT, and Wei Wang. They try to understand this genus resummation that I showed in terms of a single geometry, which is maybe not really semi-classical. Try to understand if you have just a single dual to this whole genus resummation, and they found some interesting result that seems to match in some deformed theory of geometric gravity what you get from this full genus resummation in the area limit. That seems like a pretty interesting result. I think the details still need to be nailed down a little bit, but this is a very interesting story, so I suggest you to look at that paper. Okay, so far we've been looking at values of beta that are of order e to the 2s naught over 3, and that's where the area limit is relevant. One thing you can do is go at even larger. How much time do we have? 20 minutes. You can go at even larger values of beta. So you can take beta of order, say, e to the s naught, or maybe e to the 2s naught over 3 with some large coefficient. In that case, this area analysis we did and the genus expansion that we resummed, all of that breaks down. The genus expansion diverges. The area limit doesn't quite work anymore for semi-quenched. So what you can do now is go to the dual theory, look at the matrix model, and see what happens there. So in general, you want to compute the power of z of beta to the m. So you have trace e to the minus beta h to the m averaged over this matrix model. One trivial thing you can do is take this, put it in the exponential, and define some effective potential. So if you do that, you see that if I take beta to be very, very large, this quantity, the second term, becomes of the same order of v of h. So this suggests that you have some new matrix potential, and you could have possibly some new saddle point for this matrix model. In fact, this is just a numerical plot of what happens when you take this probability distribution for eigenvalues, you multiply by 3 to the minus trace e to the minus beta h. So this is what you get near the edge. This is just area. This blue thing is once you multiply trace e to the minus beta h with beta very, very large there. And you see that you have a peak far away from the edge. So you have a high probability of having an eigenvalue separated from the rest of the spectrum. So this is just a numerical plot for intuition, but this thing can be studied quite accurately. This is what Sergio Hernandez Cuenca did in his paper. So here, I just rewrote a little bit more explicitly what we have here. So I separated the very first eigenvalue from the rest, and then you have a correction here, which goes like log 1 plus e to the minus gap between all other eigenvalues and V naught. What you can do is do an ansatz and then verify that it's self-consistent, and you can do that. With an ansatz, with the one eigenvalue separated from the rest, so that this second contribution is very, very small. So you can drop it, do the analysis, and then verify that the analysis was self-consistent, and this is indeed the case. If you compute the saddle point equations, so you want to compute where this eigenvalue is, for the first eigenvalue, you get here a contribution that goes like an additional force that is basically pushing the eigenvalue away from all other eigenvalues. And this force is proportional to beta over e to the s naught. So this thing will be order 1 if beta is over the e to the s naught, or it will start becoming important if you take beta order like much larger than e to the 2s naught over 3. So the bottom line of this story, and this can be all done explicitly and was done by Sergio, is that this is for the GUE, for example, but it works for whatever square root that you have, including JT. You have the distribution of eigenvalues that you had before, essentially unchanged, up to 1 over n suppressed corrections. But this is now only for n minus 1 eigenvalues, and one single eigenvalue separates from the continuum, and is well separated from the continuum and located at some value that can be computed explicitly. So not in, yeah. Yes, give me 2 slides. Yes, it's suppressed. It's the first subleading corrections that you need to get the correct behavior. Yeah.
Is all of this in the ARI model? Does this single eigenvalue instanton already appear in the ARI model?
Not quite. Like what you need to do, you need to go to much larger. Like this scaling is not really the ARI model. What you see is that the ARI model start, if you consider the ARI model times trace e to the minus beta h, it starts developing something that separates. So it smoothly interpolates as you increase beta more and more between the ARI models as this one eigenvalue instanton solution.
Right. I just seem to remember from memory that there was a statement that the ARI model didn't have like single eigenvalue instantons.
No, it doesn't.
And I guess here maybe something a little different is happening. You're like inputting an operator that's back reacting on the model.
That's right.
So it's a little different than the single eigenvalue instantons. Is that right?
No,
or is
sorry,
it the same
this
thing?
operator that is back reacting generates this single eigenvalue instanton saddle for the matrix model. Like it's basically enhancing, you're inserting something that really enhances outlier in the ensemble that have one eigenvalue well separated from the continuum.
Right, right. But I thought in other models, like even without inserting like some operator, you already had single eigenvalue instantons sitting at the effective
What
potential.
model are you thinking about?
Just like any higher matrix model. Is this incorrect?
I don't think you have single eigenvalue instantons. I mean, you can have maybe subleading saddles with a single eigenvalue instanton.
Yeah, that's what I meant.
Yeah. The point is that this becomes the leading saddle when you have this insertion of the operator.
I see.
Yeah.
Okay, thanks.
So if you want to compare this answer that you get from the eigenvalues and with ARI, what you can do is taking a scaling similar to the one before, but taking this, so beta over the e to the 2s naught over 3, but taking alpha much larger than 1, so some large number. And you see that at that point, you have one eigenvalue instanton separated. This is the exact formula that you get, and for the location of this instanton. And the continuum doesn't really not matter. The intuition is that the whole partition function is dominated by this single eigenvalue. So that already suggests you that the entropy will go to 0 because essentially you have only one eigenvalue. In fact, you can compute this thing. You can compute the on-shell action on this saddle, and you find that this on-shell action matches exactly the leading order that you get from ARI. So this shows you that there is a smooth interpolation between this ARI answer and then this one eigenvalue instanton answer. And the leading answer that you get for the semi-quench entropy is just 0, because you're focused on this single eigenvalue. Now, if you are not happy about that, and we were not fully happy about that, you can just ask, okay, yes, it's exactly 0, but how is it like going to 0, this quantity? In order to check that, you need to go, oh yeah, sorry, I wanted to mention that there is, for this one eigenvalue instanton, some bulk interpretation in terms of end-of-the-word branes. Also need to be some new saddle with end-of-the-word branes in the bulk, but also needs to be refined a little bit, and Sergio started doing that in that paper. So if you want to see how this entropy is going to 0, you need to look at subbleeding corrections. And it turns out that, as Roberto was pointing out, you have another saddle where instead of having one eigenvalue separating, you have two eigenvalues separating and being very next to each other but separated from the main thing. It's called a two eigenvalue instanton. And I won't go into much detail of that, but the idea is that these two eigenvalues stay very close to each other, separated from the rest. And if you compute the correction that you get, in this case, it gives you exactly the same e to the minus alpha cubed over 4 behavior of the entropy that you got in the area answer. So again, it's interpolate smoothly. It would be nice to compute the power law corrections. That's a very nasty thing to do, so we didn't, but it would be pretty interesting to see how that works. And the last thing I want to say about this beta puzzle is that, what about the quench entropy? What if you want to compute this more refined quantity? Well, from the gravity, I already discussed this non-replica limit problem. It's not very clear how to do it. From the random matrix theory, for quench, it turns out that ERI always works. So the ERI limit can be used. You can compute this thing numerically, and in some limit, you can compute it analytically, and you get an answer that goes to 0 like a power law 1 over beta cubed. What you could try to do, which is what Sergio tried to do, is computing one eigenvalue instantons and see if these capture the same answer in the matrix model. But it turns out that the one eigenvalue instanton computation, the saddle point, is only trustworthy when this quantity, e to the 2 is not over 3 divided by beta, divided by the replica index, is much smaller than 1. So if this is fine for what we did, where m is an integer and this ratio is small, but if you try to compute it in the limit where m goes to 0, in this no-replica limit, the saddle point approximation completely breaks down. And one hint of that is that the instanton is actually approaching the edge where the ERI answer should be relevant. And in that case, in fact, you get an answer that disagrees with this ERI answer that we know is correct from the matrix model. So these one eigenvalue instanton don't quite work for quench, but they do work for basically any other quantity you want to compute. Okay, maybe I have like 10 minutes left.
Sir, a few more.
Okay, I wanted to just go back a second to the second puzzle, the one including matter, and discuss a little bit what goes on in that case. So just to remind you, if you take many insertions of a single operator of scaling dimension delta, the entropy goes negative. And it goes negative for the number of insertions scaling with e to the s, if delta is large, or just with a linear number of insertions, if the scaling dimension is small. So the intuition here is sort of very similar but opposite to what we had for the thermal case. In the thermal case, we were enhancing the ground state. In this case, what you're doing is inserting a lot of operators, so you're really enhancing the largest eigenvalue in the matter operator. So again, at this level, we were computing this partition function and then computing the entropy afterwards, so we're computing some anneal quantity. A large K, so a very large number of insertions, we were again focusing on this region where the average number of eigenvalues is smaller than 1, and that's why you get a negative answer. So we need to capture really the properties and the fluctuations of eigenvalues near the highest possible eigenvalue, so again near the edge. And in order to do that, we need to be a little bit more careful than that. So this is the part which is still a little bit work in progress, so if you have any input, that would be great. To solve this puzzle, we need a matrix model which captures both JT gravity and matter. Now, this is notoriously a very complicated issue. In attempt, this was made by Jaffrey, Scholzmeier, Mukametsanov, and Sonner. It's not quite perfect. There are several things that don't quite work, but at least for the kind of calculation that we're doing, it turns out that this is enough to look at the problem that we have. So we'll just give you a rough idea of what this model looks like and the limit that we're considering and how you can use it to solve this puzzle. So when you include matter, you now have a two-matrix model, and where say that we have a single operator. This two-matrix model is a model where the two matrices are the energy and the operator that you're inserting. The potential is given by the usual JT gravity potential. If you're in non-supersymmetric case, that would be just the SSS potential for the energy. And then you have some potential which depends on the energies and on the eigenvalue of the matter operator. Now, let's consider the simplest case for now, which is this delta to infinity case, where you can eliminate, like just throw away all intersection between operators. So in this case, what you can do is essentially just have a Gaussian potential here for the matter piece. And then if you're just interested in focusing on the BPS sector, if you're in super JT, or in the given microcanonical band, what you can do is just integrate out of the Hamiltonian and integrate out all other parts of this spectrum that are not exactly where you're interested in. And what you end up with is a matrix model, which is just the GOE for the matter. And therefore, you have this equilibrium distribution density, which is just a semicircle. So this is just the simplest possible thing you can do. As you go to small delta, you're counting all diagrams the same. That corresponds to having a Gaussian spectrum. Particularly, you have a spectrum for this matrix model of matter, which is not bounded. You have an infinite tail, just a Gaussian. Now, this is true only at this specific limit where you're taking delta exactly to 0. If you don't take delta exactly to 0, but you take some small but finite delta, each intersection should be weighted by what is called the 6J symbol in JT gravity, some complicated function of the scaling dimension and the energies around the different patches, the 4 patches of an intersection. And this is something that from the matrix model side is very complicated to capture. There are a lot of issues that I don't want to discuss now. I don't have time to, but feel free to ask me later. What you can do in this case is just consider some very, very simple toy model. And that's what we did. And this toy model is what is called the Q-Gaussian matrix integral. So the idea is each intersection, instead of being weighted by some complicated function, is weighted by a constant, this constant Q. And it turns out that that corresponds to having some equilibrium density of state, some equilibrium spectral density that looks like this. It doesn't matter what the precise form is. Now, one nice thing about this Q-Gaussian is that it can actually interpolate between the GOE that you get at infinite delta and this Gaussian spectrum that you get at delta that goes to 0. So this is a plot of the Q-Gaussian distribution. As you take Q to 0, you get a GOE. As you take Q to 1, you get exactly a Gaussian. For any intermediate value, you get something that looks like a Gaussian for most of the distribution, but as you go if you go close to the edge, you get something that is a square root edge. So it's essentially a model interpolating between the GOE and the Gaussian spectrum, but it always has a square root edge for any finite Q. Yeah.
Do you allow Hamiltonian lines to intersect, or Hamiltonians with matter field to intersect?
So here what we're doing is just focusing on the matrix integral for the matter. We're essentially, you can think of it as integrating out the Hamiltonian, just focus.
So the Hamiltonian is still non-crossing lines, and Hamiltonian and the operator is still non-crossing lines.
Sorry, can you repeat that?
So Hamiltonian and itself is still non-crossing lines, like ordinary GUE, basically.
The GUE is just for the matter. The Hamiltonian still has an SSS potential.
Okay, thanks.
Yeah. So this is just a toy model for a small delta. Yep.
The double scale SYK density of states also does that, no? Is this the same? Or am I wrong?
It's very closely related. I think that this model where you weight intersections, I'm not an expert in the SSYK, I leave that to Thomas, but I think this model where intersections are exactly weighted by a constant is something that you get exactly in the DS-SYK model. For JT, just a toy model. You shouldn't take it too seriously. The toy model that turns out to have all the relevant features, which is this interpolation between the large delta limit and the small delta limit and a square root edge. But how to do that more generally in JT, I think it's much more complicated.
Can I just make a small comment?
Yeah.
I mean, in SYK, you would also have Hamiltonian coordinates. They can still intersect, and in that case, the edge is not airy, or I mean, it fluctuates much worse than anything that random matrix theory gives you.
But in the SSYK, it's true that these core rules are exactly
I mean, these are the same codes that you get, but the behavior of the edge is radically different.
I see.
The fluctuations are by a huge factor.
I see.
None of the airy computation works. So.
Thank you. Yep.
In the same spirit, so how generic is this behavior? Because you've made a number of fairly arbitrary assumptions.
Which behavior are you talking about?
Well, for instance, that you get this interpolation between the two, that you have the square root edge, that you interpolate. Is that something that's...
Okay. The model where you have large delta, you get a GOE, that's reproducing pretty accurately the JT gravity answer. Yeah. At 0 delta, you get a Gaussian, even though that's sort of a sick limit. Now the question is, okay, what's in the middle? In the middle, the correct thing to do is weight each intersection with a sig-j symbol, but that leads to a bunch of issues. For example, if you have diagrams where there is some loop, even if you fix the external energies, with a sig-j symbol, you get, I'm talking about a diagram that looks, say, something like that. Even if you fix all external energies, the energy in this patch is not fixed, and you have some integrals, so you have a mixing between high energies and low energies if you're in the BPS sector, for example. So that is something quite complicated that we don't know how to capture. So this is just a toy model that we are taking where instead of weighting this by this complicated function of the 4 energies here, you are just weighting by a constant. Now, the observation is that it seems to at least capture the correct behavior at large and small delta, and it has a square root edge. Now, the question is having a square root, all we really care about is having a square root edge in order to solve the puzzle. The question is how generic is that? That's a great question. I think having an edge, a generic delta, is believed to be true. I think several people have tried to prove the existence of an edge, and that is very, very hard to do. The fact that there is an argument that I can give you for why I think an edge is likely, and the reason is that this Gaussian potential, this Gaussian distribution that you get in the exact delta to 0 limit corresponds in the matrix model to a potential which is, let's say, marginal. So it's a potential that if you just make it slightly steeper, it would give you an edge. It's really on the marginal line of not having an edge. So including any small delta correction suggests that you would get an edge. Is that a square root edge? Hopefully. This is just a toy model. It's what we can do so far, but it's a great question.
Thank you.
Okay, now, given these models, we want to compute the semi-quantum entropy. I know I'm probably almost out of time, so I will take 3 more minutes and close. So it turns out that if you take this Q Gaussian, what you see is that there is a change in behavior when you take the number of insertion of order 1 over 1 minus Q, where Q is this parameter that weights each insertion. Q close to 1 corresponds to the delta to 0 limit. So if you take K large enough, there is a change in behavior between this linear and this log behavior that we saw in the large delta limit. So once you have that, you know that this entropy just becomes negative when the number of insertions is exponential. So we can just focus on this exponential number of insertions, and the two cases at that point are roughly equal. So when k is of order e to the 2s over 3, one interesting fact is that you can go to the area limit of this matrix potential with the insertion. This insertion is the insertion of the 2km powers, 2kn operators, to the power m in general. If you take the area limit, it turns out that you can do some manipulation such that you get an area matrix model with an insertion of something that looks like a thermal partition function. So it's basically, you are again inserting trace e to the minus beta h, roughly, where beta, this beta tilde, is dependent on the number of insertions. So once you have this, you reduce this problem with matter to the problem we had before. So the same solution applies. You have e to the 2s not, at order k over the e to the 2s not over 3, you just get the area solution that we discussed before, from the, at least from the matrix model side. If you got even larger number of insertions, you can study one eigenvalue instantons. The details will be different depending on the model, but you always have this saddle. Like the specific location of the saddle will depend if you are in the GOE, on the Q Gaussian, and so on. So this is just a plot of what this looks like. So initially you have some decay that is linear. This is a small delta case. As you take the number of insertions large, the semi-quantum entropy start going down as a log. And then here you add these area effects. That's the day. Now, this is my last slide. There is a question about what is the bulk interpretation. We did all this from the matrix model side. This is going to be a little bit speculative. We're still working out all the details of this, but I thought it was interesting, so I might mention it for you. If you have any ideas, please let me know. So this correlation function with math insertion is a sum over contractions. And as Javier pointed out before, you also have non-planar contractions in the matrix model. And you want to match these contractions, for example, in the large delta limit that I'm considering here, to some JT plus matter diagrams. Here we are throwing away in the large delta limit all interactions. So say that you have 4 insertion, you will have these planar contractions, and then you have some other contraction with a handle, and the handle is threaded by particles. So it looks like you have a one-to-one correspondence between these non-planar diagrams and this JT. But we also saw that in this area limit, we can reduce this problem with matter to a problem in a matrix model, which you can think of as just a matrix model computing the average of a partition function as some effective temperature beta tilde and not matter at all. So it seems like, and we are working out the details of this, that you can match these diagrams that you have, say, at each genus, for example, here at the disk level, these diagrams are not intersecting, you can sum them all, and that correspond to having one diagram at the disk level as some effective temperature beta tilde. So this implies that then what we saw before for the area limit in the thermal case, which is a resummation over all genus without matter insertions, works out also in this case. So this resummation of all these complicated diagrams can be written as a resummation in an effective theory where you have a specific temperature depending on the matter of insertions, but you're resumming diagrams without any matter insertion. And this seems to give you exactly the right answer. This is certainly correct just because the answer comes from the area model, and the area model corresponds to having this generous resummation that we saw before in the bulk. So this sounds like a quite interesting story to me, that you have some matrix model that includes also matter, and you can write that essentially in the area limit as a matrix model without any matter, and then consider genus resummation that gives you a positive entropy. Sounds quite interesting. I'm not sure of all the implications of this result, but that would be interesting. Yeah.
Sure. Is it a real temperature in any sense of the word? I mean, is there something that you can probe that would make
No, it's
this,
an effective temperature in the sense that it's just what you get when you take this matrix model with the insertion of matter operators. You take the area limit. You use the relation that 1 minus x over n to the n is equal to e to the minus x. You just use that, take in this area limit, and you get some thermal partition function at some effective temperature beta tilde. That's what you get out. I don't think there is any specific interpretation. It just has, it's how you map this matrix model with matter to a matrix model without matter, and the temperature depends on the number of insertions.
So it's not an emergent temperature in any... Oh.
Maybe you can interpret it. I don't know. It's a good question. It's something that we realized pretty recently, so I don't have any deep thing to say. I just thought it's interesting that you can map these two problems to each other in a very interesting way.
Yeah.
And okay, so I just wanted to leave you with a summary. So we showed that if you have a large beta, so a very small temperature, or you have a lot of insertions in JT plus matter, you get an entropy that from the gravity side, it seems like it becomes negative. And you can define this other quantity called semi-quench entropy that stays positive. And the positivity from the bulk side is rescued by these higher genus effects plus wormhole effects. And the quench entropy can be shown to be positive from the boundary side, from the matrix model, but the bulk interpretation is not quite understood. And also one eigenvalue instantons that are important to solve the first problem at very, very large values of beta are not reliable in this limit. There are a lot of future directions. Some of them have to do with analytic continuations, so computing entanglement entropies instead of Renyi entropies, or computing quench entropies, which have even more severe analytic continuation issues. From the bulk side, this is a bit of a negative result in the sense that you have some picture where the entropy stays positive, but you can only interpret it in terms of an infinite sum over many, many geometries. It would be interesting to understand if there is a way to capture this. Oh, this should have been Wayne's paper, not Wayne's talk, sorry. There was a talk about this in Benaske. So it would be interesting to understand if you can interpret this result in terms of a single geometry. And there is also a question of what is the correct model when you have generic delta in the matter case. We had this toy model that is the Q Gaussian, but just a toy model, so going beyond that would be very, very interested. And this is my one, I think every talk should have a crackpot diffuser direction. So my crackpot diffuser direction is that it would be interesting to understand if this fact that you have this positivity requirement for the semi-quenched entropy, that must be there, that is correct. So the question is, does that constrain somehow the type of wormholes that you need to include in any bulk theory dual to a matrix integral? And that seems to be the case because wormholes seem to be what is responsible for this positivity of this quantity. So it would be interesting to understand if that can be used to constrain the specific geometries that contribute to the path integral. Finally, one last thing I want to say is that all these things are not quite self-averaging. So you're really probing a regime where you're enhancing outliers in the matrix integral. So there is a question of how much of all this story can be generalized to higher dimensions, where we don't believe that there is an actual ensemble of dual theories. And that would be very interesting if you have any ideas of whether or not this kind of result generalized to higher dimensions. That would be great to hear. And that's all I have. Thank you.
So, are there more questions? I'm told it's best if we not rush to lunch, that the cafeteria may be actually quite busy right now, so.
Sorry?
For delta greater than 1, why you were saying that we are only considering diagrams where there is no crossing? Like, could you please explain that?
Yeah, the reason is that, so as I said, any intersection GT is weighted by a Cj symbol. And you can show if you take the large delta limit, the Cj symbol is essentially e to the minus delta. So if you take a very, very large delta limit, each intersection is suppressed by a factor of e to the minus delta. Which is also why, actually, maybe one thing I should mention is that this Q Gaussian toy model that I used turns out to actually be correct if you are looking at large delta, that is exactly correct. If you're looking only at large delta and only considering up to 2 intersections where you don't have this kind of loops, then that gives you the right correction because the CJ symbol is given by e to the minus delta. So 2 intersection would be an e to the minus delta. So essentially just take this Q Gaussian with Q equals to e to the minus delta. Up to 2 intersection, that's a correct model. Beyond that, it's just a toy model. Yeah.
Is there a bulk understanding of this exponential suppression of the crossings for large delta?
You mean not technical, just physical intuition?
Yes. Ideally, yes.
I think you can think of it as just coupling between matter fields, I would say. That the intersection, that the coupling for very heavy matter field is very, very small. So when you have your intersection, you have some factor of a coupling, which is extremely small. That's my intuition I have in mind at least.
And there's no notion of allowing the particles to cross in the bulk without interacting?
Not when you compute this weak contraction. No, I don't think so.
Well, why not? I mean, for example, if I just had free field operators in the bulk and I had with contractions, they'd certainly exist.
I think that interactions comes really from the back reaction of the matter insertion on the Schwarzian. So you cannot insert an operator without including also back reaction on the Schwarzian that in turns back reaction and then insertion of another operator. So I don't think you can really have insertions without interactions.
So, I mean, you're choosing a specific action here, which is, sine Louville, and you're saying everything is just given by some topological theory based on SL2, and that determines the interaction. So, when you said that you chose a specific action based in a specific way on SL2, you already chose what happens in the bulk, basically. And, choose another effective action, you'll get a different answer.
Yeah, I think the matter is that you have this interaction with the Schwarzian. The Schwarzian is the mediator of the interaction between particles.
Okay. No more questions from Mika? No? All right. Well, we had lots of wonderful discussion during the talk, so thank you again, Stefano, and we can all proceed to lunch.